Hello all and welcome to Physics with Pranav. If you're new to my channel, I'm Pranav. I used to be a CAIE Science and Maths student. I've tutored GCSE and A-level physics students from around the world, and I'm an IGCSE world topper in science from back in 2013. This video is part of a series that I'm making for the CAIE IGCSE curriculum, where for each chapter in the curriculum, I explore the key concepts that are tested by looking at data from recent past papers. I dive deeper into the concepts so you have a solid foundation of them, and then I show you how these concepts are applied to actual past paper questions. And this is what we'll be doing in this video. In particular, we'll be looking at questions from paper 4, which is a theory paper, and from chapters 6 and 7, which are around energy stores and transfers, as well as energy sources of the CAIE curriculum. I have just clubbed them together because they fall under the general umbrella of energy. I do have to point out as well that the concepts of work done and power are very closely linked to the concepts of energy. However, I will be creating a separate set of videos where I will explore the concepts as well as show how those concepts are applied to past paper questions for work done and power. But again, as I mentioned, in a lot of the past paper questions, especially in paper 4, you'll find that the concepts of energy and those of work done and power are used quite interchangeably. There's quite a bit of an overlap there. I also wanted to mention that if you're a GCSE student but are not from the CAIE curriculum, I still think you can gain a lot of value from my videos because there is still a lot of overlap between what is taught at the GCSE level for physics across the different curricula. I also think that the methodology that I will be showing you to approach past paper questions will prove useful irrespective of which of these curricula you'll be studying in. So this video on chapter 6 and 7 is one of 4 videos I've made for this chapter. If you want to check out the other 3 videos where I explore the key concepts tested, show you how they're applied to paper 2, the multiple choice paper that is, please check out the links in my description below. So without further ado, let's take a look at some paper 4 questions. So we'll start off with October number 2023, variant 4.1. The very first question is a question on energy. So they say a girl holds a rubber ball out of a window of a tall building. The mass of the ball is 0.2 kilograms. The ball is at rest 10 meters above a concrete path. So calculate the gravitational potential energy of the ball relative to the concrete path. So essentially what you've got is shown in this diagram here. You've got a girl, she's holding a 0.2 kilogram ball. It's 10 meters above the concrete path. So if you wanted to calculate the gravitational potential energy, its formula is mass into gravitational acceleration or gravitational field strength multiplied by height. I would always check what the gravitational acceleration needs to be assumed as, at the front of the paper. So usually in your very first sheet, it will ask you to take the weight of 1 kilogram to be either 9.8 newtons or 10 newtons. So it's something that you need to check. Usually if your paper is after 2023, it will be 9.8 newtons. But if it is before that, then you would have 10 newtons unless they've changed something to the curriculum. So you'll have mass multiplied by gravitational acceleration of the field strength multiplied by height. So you have a mass of 0.2, you have a gravitational acceleration of 9.81, and then you have a height of 10, which gives us a value of around 19.62 joules. So that is the amount of gravitational potential energy that the rubber ball has. The girl releases the ball and falls towards the path, the concrete path. The ball strikes the path and bounces vertically upwards, so it's probably gone down and then bounces back up a bit. Figure 1.1 shows the ball falling towards the path. So speed of the ball immediately before it strikes the path is 14 meters per second, so that is right before contact. The speed of the ball immediately after it strikes the path is 12 meters per second, so after it strikes it and it goes back up, it's 12 meters per second. So I want you to calculate the kinetic energy of the ball immediately after it strikes the path. So the kinetic energy after it strikes the path is going to be half times mass times the square of its velocity. We know its mass is 0.5 kilograms. Its mass is 0.2 kilograms, my bad. And its velocity is 12 meters per second. So if you substitute those values for the variables, you will get a kinetic energy of 14.4 joules. So that is the value after it strikes the path. Obviously, it'll be different before it strikes it because it's got a higher velocity. The question of momentum, which obviously we've covered the concepts of momentum and the questions around it in a different set of videos, so I'll not be exploring that here. So Let me see if there are any other questions around energy stores, transfers, and sources in this paper. Excuse me, got a bit of a cold. Yeah. So we've got question 5. Many methods of generating electrical power involve the use of water, which is true. So we've got a few different methods. We know of tidal energy, we know of wave energy, we know hydroelectric power. So all of these are sort of the 3 major methods that we have today to be able to generate electricity using water. So they've said, describe one method of generating electrical power from energy stored in water. So generally when they say energy stored in water, I think hydroelectric is the best assumption to make there. So hydroelectric power is a form of generating power where the gravitational potential energy of water stored in a reservoir is transferred into kinetic energy by releasing it through a dam and onto turbines at the base of the dam. So essentially you're going to have a reservoir. The reservoir is going to be at an elevated position, and because it's at an elevated position, it's going to have a store of gravitational potential energy. And then after that, the gates of the dam can be opened, and that will release water down the dam. So it's going to flow downhill. So the gravitational potential energy gets converted to kinetic energy, and then the water then makes contact with a turbine. So with the blades of a turbine. So essentially, the kinetic energy of the water is converted to the kinetic energy of the turbine, and the turbine is connected to a generator. So the kinetic energy of the generator is, or rather a coil, electric coil within the generator, results in electromagnetic induction, and that produces electrical power. So that is how you can use hydroelectricity to take stored gravitational potential energy, convert it into kinetic energy of the water, and then kinetic energy of the turbine, and finally into electrical power or electrical energy. So that is an example. For the method you chose in A, state one advantage and one disadvantage of generating electricity this way. So if you remember the chapter notes that I went through, I had created a table where I list a couple of pros and a couple of cons of each energy source. So the advantage for hydroelectricity is the fact that it's clean, the fact that it's renewable, and the fact that it's reliable. So for all of these reasons, it's really good. The disadvantage is it's quite expensive, especially the cost of construction of a hydroelectric project is quite high, and there's always flooding risks for communities surrounding a hydroelectric project. So these are 2 of the biggest risks with a hydroelectric project that we need to be wary of. So the next question is, state 2 methods of generating electrical power for which the main source of energy is not the sun. Again, many of you may have been wondering when I went through the chapter notes why I had a table which explored a few things like whether the source of energy is clean, whether it's renewable, and whether it relies on the sun. And the reason for that is because there's quite a few instances of questions where they tend to ask you either for sources that depend on the sun or for sources that don't depend on the sun, as is the case with this question. So I've said nuclear energy and geothermal energy. Nuclear energy because it depends on unstable heavy nuclei essentially breaking down into stable nuclei, and that doesn't really rely on the sun. And geothermal energy is because of hot rocks under the surface of the Earth that are being heated up by the energy from within our planet and not from the sun. So these are 2 very safe answers for sources of energy that don't depend on the sun. Let me see if there's any other questions. I think not. So let's go on to the next paper. So next paper we have is October number 2022, variant 4.3. So if I look at the questions for energy, so we have a question here. So there's a bit to the question before that. You will find again with paper 4 especially, there will be a multitude of concepts that are tested, and they are from different chapters. So something that you need to be confident and comfortable in. But essentially, you've got a tennis ball that approaches a tennis racket. The tennis ball hits the racket at a speed of 52 meters per second, so it hits at 52 meters per second. The average force on the ball during the time that it is in contact with the racket is 350 newtons. So the ball feels a force when the racket is in touch with it, and it will be in the opposite direction to the initial direction of travel of the ball. The speed of the ball after it leaves the racket is 26 meters per second in the opposite direction to the initial speed of the ball. So then it moves back in that direction with essentially half the speed that it had before. And the mass of the ball is 58 grams. So they've got a few questions around change in momentum. They want you to be able to calculate Well, they want to be able to give an equation for impulse. They want you to be able to calculate the time that the racket is in contact with the ball. So all of these are based on the chapter that we've seen before around forces in motion. But the bit that we're interested in is question B, which is around calculating energy. So it says calculate the difference between the values of the kinetic energy of the ball before and after the impact with the racket. So changing kinetic energy will be the final kinetic energy minus the initial kinetic energy. So we know that the mass of the ball remains the same. And the other thing that goes into the formula of kinetic energy is the velocity. And we know that the velocity is obviously different before and after the contact. So we've got 0.5 times or half multiplied by m multiplied by the difference in the square of the velocity. So final velocity squared minus the initial velocity squared. So we know the mass is 58 grams, so we need to convert it to kilograms to keep it in SI units, which is why I've divided by 1,000 here. And then I've got minus 26 squared minus 52 squared. So why have I got minus 26 squared, right? So this is important. So the reason for that is essentially the fact that velocity is a vector, which means it has both a magnitude or a value and a direction. So we know initially that the ball is traveling. So if we assume that traveling from left to right is positive, the ball is initially moving in the positive direction at a velocity of 52 meters per second. But then it travels in the opposite direction at 26 meters per second after collision. So because it travels in the opposite direction, that has to be denoted with a negative value. So that's why we give it minus 26. And then we subtract it from 52. And then this gives us a value of 58.81 joules, or rather minus 58.81 joules, or a total value of 59 joules. And that essentially is the difference in the kinetic energy before and after collision of the ball. So the important thing here, and the reason it's 3 marks, is obviously stating the formula correctly, doing the conversion from grams to kilograms, and just being wary of the direction of the final velocity, because it's in a different direction to the initial velocity. You need to factor that in when you are calculating the change in kinetic energy. So it's just something to be wary of, which is why the question is for 3 marks. And then if we move on to the third question, figure 3.1 shows the cross-section of a barrage built across a tidal bay. The barrage is part of a tidal power station. So you've got the gates, you've got a turbine there, essentially it's a fan of a turbine. You've got a low water level in the open sea, and then you've got a higher water level in tidal bay. So gates are raised to be open when the tide comes in. The gates are lowered to close when it is high tides, as is the case here. So figure 3.1 shows the water levels in the open sea and the tidal bay when it is low tide. The gates are raised and the water flows through the turbine. Okay, so the gates are raised and the water flows through the turbine. So complete the sentences to describe the energy transfers which take place when the gates are opened. So they've said dash energy of the dash in the dash is transferred to dash energy in the rotating dash. This energy is used in the generator to produce electrical power. This energy is used in the generator to produce electrical power. So obviously, it is more coherent when you fill it out. But with all of those dashes, it's important to be very clear how this form of energy generation works, what the energy transfers involved are, so you're able to fill these gaps out properly. So obviously what happens is, because you've got a region with essentially a higher I wouldn't say it's a higher elevation, but you've got a higher water level in one side than the other, which means the water here, as it flows, will have a store of gravitational potential energy that then it releases into kinetic energy as the water flows. And obviously, the energy is stored in the water itself. It's not coming from somewhere else. So you can say the gravitational potential energy of the water in the tidal bay, because the water level in the tidal bay is higher than the water level in the open sea. So obviously, it is the water in the tidal bay that will have the gravitational potential energy, and it's the water that will have the energy, nothing else, not the gates, not the open sea. So it goes from the tidal bay and transferred to kinetic energy in the rotating turbines. So you're going to have kinetic energy and then rotating. I think gives you the clue that turbines is what you're after. And you know that you can't start with kinetic energy of the water in the tidal bay is transferred to gravitational potential energy. That's not how it works. And usually water will flow from a higher level to a lower level, not the other way around, unless there is some pressure difference that is being acted on. So it's not going to flow from the open sea to the tidal bay in this scenario. So just something to be wary of. So state one advantage and one disadvantage of tidal power as an energy source. Again, this is just me pointing back at the table that I included in my content videos, where I had the different pros and cons for each type of energy source. So the advantage is that it's clean, it's renewable. The disadvantage is, again, with tidal, there is a high cost of construction. There is also a higher cost of maintenance, because obviously issues like rusting can be commonplace. So you have to do maintenance, and you may have to do more replacement of parts in the system. So that can be quite expensive. And state the main source of energy for tidal energy. So it's important to keep in mind that tidal energy relies on the moon, right? It's the pull of the moon that changes the tides. In fact, there's one of three forms of energy that you can give as an example that doesn't rely on the sun, directly or indirectly. So yeah, the main source of energy for tidal energy is the moon. So that's just something to be wary of. Are there any other questions on energy? No, it looks like we move on to some thermal concepts. So if we move on to the next paper, October, November 2022, variant 4.2. So, oh yeah, we got a first question, which has a link to this chapter. So, figure 1.1 shows seawater flowing down a channel into a tank without splashing. So that's seawater, it's flowing into a tank. The water is flowing at a rate of 800 kilograms per minute. That's the mass flow rate. The length and width of the tank are 3.1 meters and 1.2 meters respectively. So that's 3.1 and 1.2. And the density of the seawater is 1020 kilogram per meter cube. So it's slightly more than the density of your pure water. So initially the tank is empty. Calculate the depth of water in the tank after a minute. Give your answer to three significant figures. So we've seen a couple instances where we've had to link the concepts of mass flow and volume flow, and we have to link the concepts of mass, volume, and density together to be able to calculate one of the missing quantities. And it seems to typically be linked to questions around energy calculations. So it's just something to become wary of, because we definitely saw it in a multiple choice paper. So if you look at my video link for the paper 2, there is definitely a question where you have to calculate volume flow. So in this case, though, they are interested in the depth of the water. So the depth will depend on the amount of volume that's flowed in, and the amount of volume that's flowed in is going to depend on essentially the mass of water flowing in and the density of the water, both of which are quantities we have. So we know that the volume is the area multiplied by the depth. So the area would be the length multiplied by the width, and then you're going to have the height, which is the depth, which will give you the volume. We know that the volume of water flowing in is going to depend on the mass of water flowing in divided by its density. So we know the mass flow rate. So we know that essentially we have the mass flow rate multiplied by the time. So we know the amount of mass flowing in because we have a flow rate, which means the mass per unit time, and then we multiply by the amount of time that it's flowing in for. So that's going to give you the total mass flowing in. And then we have the density as well. So density is 1020 kilogram per meter cube. We know that the mass flow rate is 800 kilogram per minute, and we want to calculate the depth of water after a minute. So the water has been flowing in for a whole minute, which means the mass of water that would have flowed in would be 800 kilogram per minute multiplied by a minute. So you'd have essentially 800 kilograms of water that would have flowed in a minute, and the density of the water is 1020 kilogram per meter cube. So this gives us a volume of 0.78 meter cubes that would have flowed in that minute. And then we know that the volume is the area, which is the length multiplied by the width, and then that multiplied by the depth. So we can calculate the area quickly by multiplying these two quantities out. And if we rearrange the equation, now that we know the amount of volume that's flowed in a minute, and we know the area, if we rearrange the equation for depth, we get a depth of 0.21 meters. That's the depth in the tank of water after it's been flowing for a minute. The second part B says calculate, so the height of the water decreases by 0.42 meters as it flows down the channel. Calculate the decrease in gravitational potential energy of the water each second. So we know that the gravitational potential energy is the mass multiplied by the gravitational acceleration or the gravitational field strength multiplied by the height. So essentially here, we want to see the loss or the decrease in gravitational potential energy because the height is decreasing. And we know the total amount by which the height decreases, which is 0.42 meters. And we want to know the decrease in gravitational potential energy each second. Because we know that we have a flow of mass and it's not a constant mass. It's the flow of mass that's going to give us essentially how much the gravitational potential energy is decreasing every second. So we've got mass flow rate per second. Remember though that we said it was 800 kilograms per minute. So if that's per minute, a minute has 60 seconds. So each second, if we want to find out the amount of mass that's flowing, we divide 800 by 60, which is what I've done here. And I multiplied by the gravitational acceleration of the field strength, which is 10. Again, this is a pre-2023 paper. It's October number 2022. So pre-2023, you would have a gravitational field strength of 10, and then we have a height of 0.42 meters because that's the height by which the water decreases as it flows down the channel. So essentially, the change in potential per second is 56 joules. So the decrease in gravitational potential energy is 56 joules, which is what we've got here. So it's a question on pressure, which we're not really looking at. So hopefully that made sense, that question there. A bit around mass flow and volumetric flow, and then obviously a question around gravitational potential energy changes. Usually energy calculations will be either on gravitational potential energy changes, kinetic energy changes, or efficiency, which we'll look at as well. We'll look at some questions around efficiency. So the next question on chapter 6 and 7 is question 3. Excuse me, I've got a bit of a cold, sorry. So tidal power derives most of its energy from the moon and part of its energy from the sun. So state one of the source of power which derives its energy from the sun. So the most obvious one is solar. Solar energy literally relies directly on the sun. And then state one source of power which does not derive energy from the sun, and that's nuclear. So that is fairly straightforward. Again, if you take a look at the table that are provided in my content videos, I think it'll prove really useful because ultimately you will get at least a mark's worth of questions on this topic in paper 4s and in paper 2s as well. So it's worthwhile, getting those easy marks. So part B goes, figure 3.1 shows a small water turbine driven by the tidal flow of water to generate electrical power. That's the surface of the sea, there's a seabed, you've got like a turbine here, and then you've got the water flowing that way. Explain whether this method of generation of electrical power is renewable. So it is a renewable source of energy because the flow of water in the sea will not be exhaustible as it is generated by wind and currents, both of which are also not exhaustible as long as the sun is there. As the source of energy can replenish itself, it is renewable. So you're not going to, as long as the seas are there and global warming doesn't like boil them all off, and as long as the sun exists and doesn't disappear, you're essentially going to have currents. You're going to have winds, which is going to result in waves. And obviously you're going to have sea currents as a result of that. And as long as you have, like I said, oceans and the sun generating it, the water is going to obviously replenish itself, and it's going to be a renewable source of energy. It's not going to run out once it's used. So in part 2, there's an interesting calculation question. The mass of water passing through the turbine each second is 6 × 10⁻³ kg, so essentially 6,000 kilograms per second. The speed of the water is 2 meters per second. 40% of the kinetic energy of the water is converted to electrical energy, so calculate the electrical power generated. So the first thing that we need to keep in mind is we need to calculate first what the input energy into the turbine is. So the input energy is kinetic energy. So first, if you wanted to calculate the kinetic energy, that's going to be equal to half, or 0.5 multiplied by mass multiplied by the square of the velocity. So we know that that's going to be half multiplied by 6,000 multiplied by 2 squared, because that's the velocity. And that gives us around 12,000 joules every second. We know that only 40% of the kinetic energy is converted to electrical energy. So we multiply that value by 40%. So that gives us around 4,800 joules every second is converted into electrical energy by the turbine. And as the water passes through every second. Essentially, we're looking at a concept of power, because energy transferred or work done per unit of time is power. We know that that's the amount of energy that's transferred every second. So because that's transferred every second, 4,800 joules per second, this is essentially 4,800 watts or 4.8 kilowatts. So power is 4,800 watts. So again, I know we still haven't explored the concepts of power as of the making of this video, and I will be making videos on work done in power. But as I've mentioned a few times in my videos on this chapter, you will find that there are a lot of questions interchangeable between energy and power. There's a lot of overlap between the concepts. So you will find that when we do past paper questions on the concepts of power and work done as well, they will have quite a bit of overlap with the concepts that we've learned in energy. So it's just something to keep in mind. And I think it's a lot more common as well in paper 4, where concepts are tested, or different concepts rather, are tested in the same question. So it's just something to be wary of. Any more questions? No, there's a lot of questions around thermal properties, so no more questions on energy. So if we move on to the next paper, we're now looking at October, November 2021, variant 4.3. It's a nice kinematics question there. Sorry, there's a bit of a lag in my screen as we go down the PDF. So question 2, figure 2.1 shows a simplified version of a gravity lamp. This apparatus is used to light a light-emitting diode without mains electricity. Okay, so you got a lamp, it's attached to a ceiling, you got a generator, 12 kilogram load, and it's strapped essentially to the generator, and then there's an LED there. Right, the load of 12 kilogram is raised to a height of 1.7 meters above the ground, so there is 12 kilogram load. So if that's the ground, for example, it's probably raised up 1.7 meters above the ground. The load is connected to a pulley system. The time taken for the load to fall to the ground is 1,200 seconds. So to fall a distance of 1.7 meters, it takes 1,200 seconds. And the load falls at a constant speed. So technically the load will accelerate because you have the Earth's gravitational field pulling against it, but they have asked us to assume constant speed, so that's important. And the generator is connected to an LED. So I'm guessing as the load falls, it's gonna, it's gonna result in a coil turning somewhere. That's going to result in electromagnetic induction. Obviously, these are concepts we'll be exploring when we look at electricity, and then that is going to result in electricity being supplied to the LED, and that glows up. So calculate the rate of transfer of gravitational potential energy as the load falls to the ground. So they want the rate of transfer of gravitational potential energy, right? So firstly, then, we need to know two things. We need to know, firstly, how much gravitational potential energy is transferred, and we need to know over what period of time, because we're concerned with the rate. So if you think about the gravitational potential energy of the load, or the gravitational potential energy it rather loses when it falls to the ground, that's going to be equal to its mass multiplied by the gravitational acceleration or the gravitational field strength multiplied by its height above the ground. So we know it's got a mass of 12 kgs. We're going to assume a gravitational field strength of 10 meters per second squared, and then we are going to have a height above the ground of 1.7 meters. So if you multiply those out together, you get a value of 204 joules. The next thing that we're interested in is the rate. So that's the amount of gravitational potential energy that is transferred as the load falls, and this happens over a period of 1,200 seconds. So if I divide the amount of energy transferred by the time, that essentially gives me the rate of transfer, which is 0.17 joules per second. And we know that the rate of energy transfer, the rate of work done, is power, and power has the units of watts or joules per second. So essentially we have a value of 0.17 watts. So that is the rate of transfer of gravitational potential energy in this scenario. Have you got any more questions on the concept? Yes, we do. We've got a question on efficiency, which is something we covered in the concepts we haven't seen in paper so far. So this is a nice example. The light output of the LED is 0.1 watts. So calculate the efficiency of the lamp. So essentially, the light output is what you want from the LED, because a light emitting diode, its purpose is to emit light. That's the useful output. The amount of input that you get because of the falling load is 0.17 watts. So the efficiency is the energy, the useful energy output by the total energy input, or the useful power output by the total power input. So we know that the power output essentially or the useful power output is 0.1 watts. We know the power input is 0.17 watts. So that gives us a value of 0.59 or 59% essentially. You multiply the decimal value you get there by 100, and that gives you the percentage efficiency. So that is something to have. Or sorry, what I mean to say is that is how you would calculate that. And then the next question says, suggest a social or environmental advantage of using a gravity lamp. So you're not using mains electricity, so it's not a lamp that's plugged to the main source. And usually the main source in most countries is supplied either by a coal plant or a natural gas power plant. And these are, firstly, they are non-renewable source of energy. Secondly, when you burn coal or natural gas, it releases greenhouse gases like carbon dioxide. It can, especially in the case of coal, it can also release a lot of particulate matter. It can also release, due to incomplete combustion, it can also release things like carbon monoxide and nitrous oxides. So all of these obviously are not good for the planet. It's not good for the people who work in the plants. So that is a social and environmental disadvantage. But when you use a gravity lamp, you are literally just relying on the force of gravity that the Earth exerts on a load to be able to generate the electricity that is then used in the lamp. So essentially it is good for the planet, and it's also it's good for, I suppose, like no one is working in environments where they're exposed to particulates and gases like carbon monoxide. So that's the advantage of that. Just checking again if there are any further questions of interest. No, I think we've gone into thermal properties and thermal concepts. So if you move on to our last paper that we'll be looking at, which is October, November 2021, variant 4.2. Again, I could see there's some questions on kinematics. It's a question on Hooke's law. It's a question on momentum and impulse. And yeah, so we've got question 4. A power station uses wind energy to generate electricity. State and explain whether this method of generating electricity is renewable. So wind energy is a renewable source. The statement is that yes, the wind energy is a renewable form of generating electricity. And the explanation is it uses wind. Wind is replenished, again, as I said, as long as we have an atmosphere on the planet, as long as the sun shines. Different areas on the surface of the Earth get heated by different amounts because of, I suppose, some areas are slightly closer to the sun. Some areas have a slightly thinner atmosphere. So obviously there are these different weather patterns that arise, the different like wind currents. And as long as the sun heats different parts of the surface of the Earth differently, and as long as we have an atmosphere, you will have wind currents. So it is a renewable source of energy. State 2 energy sources that do not have the sun as their source. Again, you see this repeating in a lot of papers, so it's very useful to keep this in mind. So nuclear and tidal are good contenders. You can also say geothermal. For each energy source, state the form of energy stored in. So you've got fossil fuels, you've got chemical energy that's stored in them, and you've got water behind dams, and you've essentially got gravitational potential energy of the reservoir. The chemical energy, when it's burned, the bonds break, and that energy is released into usually like thermal energy, but then it can also be used to essentially probably a bit of light if the object that is being burned glows. There's definitely going to be heat, and it can obviously be used to generate electricity. The same with water behind hydroelectric dams. They've got gravitational potential energy, which is then converted to kinetic energy and then potentially electrical energy. So again, we could see that afterwards we got concepts around waves and thermal properties of matters and things like that. So that is essentially all the questions we're going to look at for paper 4. I hope you've got a flavor for the types of questions you can get, both on energy sources as well as energy stores, transfers, energy calculations. We also saw a question on efficiency. We've seen how the concepts of the rate of transfer of energy, i.e. power, which we are still to explore at the time of making of this video, but I will make videos on it, is closely linked to the concepts that we experience around energy. And as you'll see when I make videos on that topic, you will find that a lot of what we've learned in this chapter also applies there. But anyway, I hope you found this video useful. If you did, Please like, share, and subscribe. And yeah, again, feel free to check out, if you haven't already, the content that I made for this video, or that content being applied to paper 2. Again, the links are in the description below, so feel free to check it out. And yeah, thank you for watching, and I'll catch you in my next video.